Oh 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 oh. I've been on death row for 5 years now. Plenty of time to think about all of the horrible crimes I have committed. But the thing I am most ashamed of, the thing I regret the most, is not how I killed all of those innocent people. It's how I never learned how to use the ordinary least squares estimator. Let me tell you about a brighter time in my life, when I was a carefree financial econometrics student. Let me take you back to the financial adventures I had with my friend Henry.
Hey Simon. Have I ever told you about regression?
No. No, you haven't, Henry. What do you mean by regression?
Regression analysis seeks to describe the relationship between a given variable and any number of other variables.
Oh, that's easy. You just mean correlation, don't you?
Not quite. Let's go outside and I'll explain the difference between regression and correlation. Great weather today, eh? Do you see all of those people in the park?
Yes.
Let's pretend our two variables are 1. Today's temperature, and 2. The number of people eating ice cream in the park. Would you expect the two to be correlated?
Yes, of course. There would be positive correlation. More people will eat ice cream when it's hotter.
Exactly. Correlation tells us that there is a relationship. However, it does not tell us exactly how one variable changes with respect to another. In regression, the question we are asking is, if the temperature were to increase by 10 degrees, how many more people would we expect to see eating ice cream?
Oh, I get it. We want to estimate the linear relationship between variables. If we were to observe a change in x, then what change would we expect to observe in y?
However, when we make observations in the real world, we never see nice, exact relationships. Our data will look something like this scatter graph. This graph could represent our analogy in the park, or we could be comparing two stock indices, such as the S&P 500 and the FTSE 100. It looks like there's a relationship, doesn't there?
Indeed. I could just draw a line through the middle of those points and then we would be finished.
But Simon, that wouldn't be a very accurate method. This is where our ordinary least squares estimator comes to the rescue. We want to create a linear model in the following form. Notice that we've added a noise term, UT, to account for random disturbances in our data. This is what our noise terms look like on our graph. They are the vertical distances between our data points and the regression line.
But Henry, why must they be the vertical distances?
Because we are assuming that when we take many samples of our data, the x variable has fixed values, whereas y contains a random element.
So naturally we want to minimize these random residual terms.
Spot on. To do this mathematically, we want to minimize the sum of the squared residual terms. The residual sum of squares is to be minimized. Yt is our data point, whereas yt hat is the value that our linear model would have predicted.
So we want to calculate the coefficients alpha and beta which will minimize this sum. How do we do this, Henry?
My friend Isaac Newton might be able to help.
Henry, my friend, I have invented a way to solve this problem. Simply differentiate with respect to alpha and beta, and set this equal to 0.
Excellent. Doing that gives us the following formula for the ordinary least square estimators.
So when we use these values for the intercept and slope of our regression line, we minimize the residual sum of squares.
Correct. Now, please go away.
We use the OLS estimator because it has some important qualities. Firstly, it is the best, or most efficient estimator, meaning that it has the smallest possible variance. It is also a linear estimator, and it is unbiased, meaning that on average, our estimates will be equal to the true values.
It sounds perfect to me.
Don't get carried away, Simon. Any regression estimates rely on our sample data, so we have to ask how confident we're with our estimates. Here are the standard errors of our estimators alpha and beta. These tell us the likely accuracy of our parameters.
So we want these standard errors to be small.
Yes. If they are small, then a regression coefficients are more likely to be precise on average.
Thanks, Henry. There's a lot to remember here.
Good luck, and happy regressing.
Oh, I wish I had paid more attention to Henry. Maybe if you learn about the OLS properly, then you won't end up in prison like I did. Don't make the same mistakes as I Dear listener,